Hi everyone, today we're going to be talking about topic 6.2, energy diagrams. Now in our last video, we talked about these two types of reactions, exothermic and endothermic reactions. As a reminder, an exothermic reaction is one where the system transfers heat, or Q, to surroundings. Right? And so if your system has some associated amount of thermal energy, that thermal energy goes to your surroundings. And an endothermic reaction is the exact opposite. The surroundings will transfer heat, or Q, which is our symbol for heat, to the system. Right? And so heat goes into the system for endothermic, and heat leaves the system for an exothermic reaction. We can express that using what are known as energy diagrams, which can help us determine whether or not we have an exothermic or an endothermic reaction. So in an exothermic reaction, we can draw a diagram that looks something like this. We can have our y-axis. This is our energy. And this represents energy as increasing. In these diagrams, the units don't really matter. All we care about is what the diagram looks like. Over here, we have, so energy is going up on the y-axis. This is the direction of the reaction. So there are no units associated with this. This isn't a graph in the sense of you're trying to measure something and collecting data. This is a diagram in the sense to show you what a reaction is looking like, depending on if it's exothermic or endothermic. In the exothermic case, what will happen is we'll have some sort of energy here, right? This will be the energy of the reactants. This is where we start. You'll have the reaction will take some amount of energy. You'll essentially increase in energy. This difference here between the maximum energy and where you start, this is your activation. Let me give myself a little more space here. This is your activation energy, which you'll sometimes see me writing as E with the subscript A. The activation energy is just equal to the amount of energy required for the reaction to proceed. And so your reactants have some sort of an energy. Of course, the number does not matter, right? All of this is just qualitative. They start with some sort of energy. You require a certain amount of energy for the reaction to occur. And in the exothermic case, the energy of your reactants, of your products, is going to be lower. And so where you end is the energy of the products. In the case of an exothermic reaction, this will be lower than where you started, or the energy of the reactants. Now what we can do is we can draw this little dotted line here, and the difference between those energies is the energy that is released. Right, and so in the case of an exothermic reaction, that difference in energy is the energy released. For an endothermic reaction, you can imagine it's the exact opposite case. And so we'll still have energy on our y-axis, and we'll have the direction of the reaction on our x. And of course, the reaction goes to the right. In this case, the energy of our reactants is going to be lower than the energy of our products, and it's going to take some amount of energy for that reaction to occur. So here we will have the energy of the reactants Here we have the energy of products. This will be our activation energy, which in this case is just the difference between the start and that peak in your energy. And this right here, the difference between energy of reactants and energy of products. In the case of endothermic, because now your products are higher energy, this is the energy absorbed by the reaction. So this is a visual way of showing an endothermic and exothermic reaction. Now there's one additional definition that we can make, and it's something that we're going to come back to for the entirety of AP chemistry here on out, and that is known as enthalpy. And so enthalpy is equal, and we call this H. That is equal to the heat flow during a reaction. And in general, we're always measuring delta H, or the change in heat flow. That's what we're always interested in measuring. We don't normally measure H on its own. So the enthalpy will measure the heat flow during a reaction. We can also define the enthalpy of reaction. So the enthalpy of reaction is the difference of the energy of the products and the energy of the reactants. What we normally define that as is delta H, so the change in enthalpy, and then as a subscript reaction, Rxn. So the change in enthalpy of the reaction, and the units for that are typically going to be in kilojoules per mole. Right, we can also write that as kg times mole to the -1, right? Kilojoules per mole. And so now we're thinking about energies. Energies are always in joules or kilojoules. Now, if you want to measure the delta H, the change in enthalpy of a reaction, that's going to equal the sum of delta H of formation of the products minus the sum of the delta H of formation of the reactants. And we'll do an example later, but the change in enthalpy of the reaction, or the enthalpy of the reaction, is going to be equal to the sum of delta HF of products minus the sum of delta HF of reactants. And again, if delta H of the reaction is positive, therefore this is an endothermic reaction. So after I do this calculation, if I get a positive number, it's endothermic. If delta H of the reaction is negative, then this is an exothermic reaction. We can also show this in the context of an energy diagram. So in an energy diagram, if the products are higher energy than the reactants, you have an endothermic reaction. And so this is that example of an endothermic reaction, right? The products are higher in energy. That difference between the products and the reactants that's a delta H, and it'll be positive because it goes up. The exact opposite is true for an exothermic reaction. For an exothermic, the reactants are higher energy than the products. This delta H will equal a negative number. This would be a positive number in that case. So let's do one quick practice problem together doing this enthalpy of reaction calculation. So you're told that you have this combustion of C2H4, and it's done in the presence of O2 gas. This makes 2 carbon dioxide and 2 water, and what you're trying to do is find the enthalpy of formation of the reaction, or the enthalpy of the reaction. And so what we're typically given in this is we're given a table of enthalpies of formation. This is the energy required to actually form that particular reactant or product. And so what you can do, remember the equation, delta H, our enthalpy of reaction, is equal to the sum of the delta H formation of products minus the sum of delta H of formation of reactants. Therefore, delta H of the reaction is going to equal our products, our CO2 and H2O, our reactants, our C2H4 and 3O2. What we got to remember is to always multiply by our coefficients. And so this is going to be, and I'll just do it quickly in symbol form, this is going to be delta H of formation, or 2 times delta H of formation of CO2, plus 2 times delta H of formation of H2O. All of this will be subtracted by the reactants, which will be the delta H of formation of C2H4 plus the delta H of formation of O2. And we multiply that by 3 because there's a subscript 3. All right, so we're going to find each of those terms, and then we're going to do that final subtraction. So I'm going to do it down here in this little white space. Delta H of the reaction is going to equal, I'll do my bracket, 2 times negative 394 kilojoules per mole, plus I have 2 times H2O, which is negative 286 kilojoules per mole. All of that is going to be subtracted by the reactants. For C2H4, we have 52 kilojoules per mole, and that is plus 3 times 0. And generally, the delta H of formation of elements is always going to be 0. And so if we do all of that math out, the delta H of your reaction is going to equal negative 1,412 kilojoules per mole. And this would be an exothermic reaction. So if I burn C2H4 in the presence of oxygen, I make carbon dioxide and water, and that reaction is going to release heat into the surroundings. It's exothermic. We'll work on some more practice in class, but for now, that's all. Thanks, guys.